Good morning everyone. Today we will discuss about carboxylic acid. Introduction. Carboxylic acid are acidic compound having one or more carboxylic group. C double bond OOH or C double bond COOH in their molecule. The name carboxylic is derived by the combination of a term carbonyl C double bond O and hydroxy OH, since the group C double bond OH may be looked upon a combination of a carbonyl and a hydroxyl group. The carboxylic acid are classified as mono-di-tricarboxylic acid according to the number of a carboxyl group present in the molecule. Thus, monocarboxylic acid may be represented as RC double OH, where R is be a simple or substituted alkyl or allyl group. However, the properties of a carbonyl group are essentially the same irrespective of aliphatic or aromatic nature of a group attached to it. Nomenclature. First, common system. The aliphatic monocarboxylic acid are commonly called fatty acid, as many of them, particularly the higher member, occur in a natural fat. The common name of the individual fatty acid are derived from some of their natural sources. For example, formic acid is some of a name as it was originally obtained by distillation of formica ant. Similarly, acetic acid derived its name from acetum vinegar in which it is present. Branch chain acid have only one branch of a methyl group, fastest always from the carbonyl group, are named by adding the prefix iso to the name of a corresponding state chain acid. For example, CH3CH, CH3CH2, OH O double bond O is known as isoverneric acid. Other branch chain acid or substituted acid are named as appropriate derivative of a straight line acid. The position of a side chain or substituted group being indicated by the letter alpha, beta, gamma, etc. Examples are given below. Aromatic acid having the carbonyl group directly attached to aromatic nucleus are generally referred to an derivative of benzoic acid. For instance, chlorobenzenoic acid is known as para-chlorobenzoic acid. Some of these acids are, however, also known by special names, as for example, methyl benzoic acid are generally called toluic acid. IUPAC system. The IUPAC name of a carboxylic acid are obtained in accordance with the generally IUPAC rule. The suffix used for a carbonyl group being oic acid. For naming opening chain carboxylic acid, the name of parent hydrocarbon corresponding to the longest possible chain in molecule is written. The finally E of the name of a replacement of oic acid and the word acid is added. In numbered the carbon of a straight chain, the carbon of a carboxyl group which is present at end of the chain, always numbered 1, while side chain, if any, get other substitutable number. For example, 3 methyl butanoic acid, 2 methyl pent 3 enoic acid. Carboxylic acid having a carboxylic group attached to a cyclic ring are named by adding the suffix carboxylic acid to the name of a ring. The carbon atom of a ring carrying the carboxylic group is always taken as number 1. For example, cyclohexane carboxylic acid, cyclohexane 2 in carboxylic acid, 3 cyclohexane cyclopentane carboxylic acid. The simplest aromatic carboxylic acid, benzenoic acid. Other aromatic acids are named as derivative of benzoic acid. Salt of carboxylic acid are named by writing the name of a cation followed by the name of acid in which the end ic acid has been replaced by a OAte. For example, sodium acetate. ammonium butyrate. The common and IUPAC name of some carboxylic acid are given in table 5.1. Structure of a carboxylic group. Acidic character of a carboxylic acid. Even though the carboxylic group is generally represented by the structure C double bond O OH. Actually, it is a resonance hybrid of the following contributed structure. However, this is separated by charges in structure second, and therefore it is less stable than structure first. As a result, these structures do not make equally contributed to a resonance hybrid. Contribution of a structure second being much less important than that of first. Consequently, the resonance energy is quite low. It is evidence that in the resonance hybrid, oxygen of a hydroxy group carrying some positive charge. As a result, the electron pair of a OH group is largely displaced toward oxygen. Due to this displacement of electron pair, the hydrogen of OH bond can be released as H positive ion with the stimulus formation of a carboxylate ion. This is responsible for acidic nature of a carboxylic group. Now the carboxylate ion formed by the ionization of a carboxylic acid is also a resonance hybrid as shown ahead. It can be easily seen that the two contributing structure of carboxylate ion third and fourth are equivalent to each other, and therefore they make equal contribution to resonance hybrid. As such, the resonance energy of carboxylate ion is much greater than that of acid itself, for which the contributions did structure different considerable in their energies and do not make equal contribution to the resonance hybrid. In other words, the resonance stabilization of a carboxylate ion is much more than that of a carboxylic acid. This greater stabilization of a carboxylate ion tends to push the equilibrium in the ionization process toward the right, and thus constitutes the major factor in dissociation of a carboxylic acid. Since the carboxylate anion is an resonance hybrid of two similar structures, third and fourth, it may be seen with Vlies as equivalent to structure 5. This means that the negative charge is evenly distributed over both the oxygen atom. Both the carbon-oxygen bond are equivalent, and each is intermediate between single and double bond. This depiction of a carboxylate ion is confirmed by the X-ray diffraction studies of a bond length of a carboxylic acid and their anion. For instance, it was found that in formation formate ion used in the form of a sodium formate, both carbon-oxygen bond length having the same value, 127 picometer or 1.27 angstrom. This is possible only if both carbon-oxygen bond of the ion are exactly equivalent. On the other hand, formic acid gives two different values of carbon-oxygen bond length, 123 picometer or 1.23 angstrom for carbon double bond oxygen length, and 136 picometer for carbon oxygen bond carbon and OH bond length. This shows that in formic acid that carbon double bond O has greater double bond character, while carbon OH bond has greater single bond character. Orbital structure. The resonance in carboxylate ion can also be understood in terms of a molecule orbital concept. In the term of this concept, the carboxylic group atom is in a state of sp2 hybridization. These hybrid orbital are directly toward the corner of a triangle and lie in the same plane at an angle of 120 degree with each. These three orbitals form 3 sigma bond on each with the 2 oxygen atom and a third with the alpha carbon atom or H atom in case of a formation of ion. The remaining unhybridized p orbital of a carbon overlaps sidewise with the p orbital of both the oxygen atom to form a delocalization of a pi molecular orbital. In other words, the pi electrons are not confined to the nuclei of two atoms but get distributed around the nuclei of three atoms. This delocalization of a pi electron leads to the stabilization and ace of the formation of a carboxylate ion. Comparison of acidic character of alcohol and carboxylic acid. Both alcohol and carboxylic acid containing OH group in their molecule, but alcohols are partially neutral compound while carboxylic acid having acidic character. This is due to the fact that carboxylic acid contain carbonyl group attached to a hydroxy group. This enables both carboxylic acid and carboxylate ion to exhibit resonance, with the latter being more stable than the former. As a result, carboxylic acid gets dissociated to form H positive ion and carboxylate ion. On other hand, neither alcohol nor alkoxide exhibits resonance. Therefore, they do not dissociate to an appreciable extent and are practically neutral in character. Comparison of acidic strength phenol and carboxylic acid. Carboxylic acid are stronger acidic than phenols. This can be explained in terms of a stability of a carboxylate and a phenoxide ion. On comparing the structure of a carboxylate ion and phenoxide ion, we find that the negative charge on a carboxylate ion is dispersed over two oxygen atoms, while in phenoxide ion it is present on one oxygen atom only. The charge dispersal on two oxygen atoms lead to greater stability and therefore greater ease of a formation of carboxylate ion. Therefore, carboxylic acid can release H positive ion more easily and are stronger acids than phenols. General method of preparation. The important method of preparation of carboxylic acid are discussed below. First, oxidation of a primary alcohol or aldehyde. Carboxylic acid can be readily obtained by the oxidation of a primary alcohol or aldehyde. The usually oxidizing agent employed are acidified for potassium dichromate, potassium permanganate, or a nitric acid. Primary alcohol or aldehyde in presence of oxygen give carboxylic acid. Aldehyde can be oxidized to corresponding acid even by mild oxidizing agent such as toluene reagent. For example, aldehyde plus toluene reagent give carboxylic acid. This method is highly selective as it will not oxidize any other oxidizable group such as alcoholic group if present in a starting aldehyde. Second, oxidation of alkyl benzenes. On heating alkyl benzenes with oxidizing agents such as acidified potassium dichromate or acidified or alkaline potassium permanganate, the alkyl side chain get oxidizing to carbonyl group. The reagent commonly employed is alkaline potassium permanganate. The constituent a useful method for the preparation of aromatic acid as the alkyl side chain is always oxidizing to carboxylic group irrespective of its size. Alkyl benzene in presence of oxygen give benzoic acid. Third, hydrolysis of nitriles. Hydrolysis of nitriles with aqueous acid or alkaline is an important method of preparation of carboxylic acid. Nitrile plus water in presence of H positive or OH negative give carboxylic acid plus amines. Sorry, ammonia. Aliphatic nitriles can be themselves readily obtained by the treatment of alkyl halide with sodium cyanide. Therefore, formation of a nitrile followed by its hydrolysis afford a useful method of preparation. A carboxylic acid containing one carbon atom more than was present in a starting alkyl halide. Aromatic nitrile, it may be noted, are obtained from diazonium salt as discussed later in chapter 11 and not be reaction of aryl halide with NaCN. Mechanism. Acidic hydrolysis of a nitrile take place as follows. Alkene hydrolysis of a nitrile proceeds as follows. Fourth, hydrolysis of acidic derivatives such as acid chloride, anhydride, ester, amides. The acid derivative mentioned above can be hydrolyzed to produce carboxylic acid with varying degree of difficulties, while acid chloride and acid anhydride are hydrolyzed with water. As such, hydrolysis of ester and amide is carried out in the presence of a mineral acid or alkynes. As a practical method of preparation of carboxylic acid, hydrolysis of acid derivative is seldom used because acid derivatives themselves are very often prepared from acid. However, hydrolysis of two natural occurring classes of acid derivative, oil, fat, or protein, is employed for the preparation of a certain acids. Mechanism. The mechanism of acid and alkyne hydrolysis of acid derivative is discussed later in chapter 6. Fifth, carbonation of a Grignard reagent. Carboxylic acid may be present by the reaction of Grignard reagent with carbon dioxide followed by decomposition of the addition product with dilute mineral acid. The reaction is often referred to as carbonation of Grignard reagent. Carbon dioxide may be employed either in the gaseous form or preferable in the form of a solid ice. Grignard reagent plus CO2 in presence of ether give additional product, and in the presence of H3O positive give carboxylic acid. Mechanism. The mechanism of addition of a Grignard reagent to carbon dioxide is similarly to that of addition of aldehyde and ketone. The nucleophilic organic group of a Grignard reagent acid to electrophilic carbon to carbon dioxide, while the MgX part goes to one of the oxygen. Like the nitrile reaction, Grignard reaction also yield a carboxylic acid containing one carbon atom more than alkyl halide, from which Grignard reagent is obtained. Organolithium compound can also be used in place of Grignard reagent in the synthesis of carbonyl carboxylic acid. Sixth, malinoic ester and acetoacetic ester synthesis. Mono or dialkyl derivative of acetic acid can be easily obtained by a malinoic ester or acetoacetic ester synthesis as discussed below. Malinoic ester synthesis, diethyl malinoate CH2 bracket C double bond O C2H5 twice, generally referred to as malinoic acid ester, forms its sodium salt on reacting with metallic sodium or sodium ethoxide. The sodium salt in a trans can be easily alkylate on treating with alkyl halide to form alkyl derivative of malinoic ester. Malinoic ester in presence of sodium ethoxide give sodium malinoic ester. In presence of RX give alkyl malinoic ester. Alkyl malinoic ester can be similarly converted into dialkyl malinoic ester. The mono or dialkyl derivative of a malinoic ester may be hydrolyzed to form mono or dialkyl derivative of malinoic acid, such that RCH C double bond OOH twice or RR-C COOH twice. These acids in turn can be decarboxylate by heating of or to yield mono or dialkyl derivative of acetic acid, RCH2COOH or RR-CHCOOH. Thus we have a proper choice of alkyl halide or halide to get the hydrolysis or dialkyl malinoic ester can help to obtain practically even acid by means of a malinoic ester synthesis. For example, let us say that it is desired to prepare N-valeric acid CH3CH2CH2CH2COOH. This acid may be regarded as N-propyl derivative of acetic acid. Therefore, we should first convert sodium malinoic ester into N-propyl malinoic ester by reacting with N-propyl halide and subsequently hydrolyze and decarboxylate the alkyl derivative to get the desired product as shown ahead. Acetoacetate ester synthesis. Like malinoic ester, acetoacetic ester can also be converted into mono and dialkyl derivative of acetic acid. Monoalkyl derivative of monoacetic ester on acidic hydrolysis yield a molecule of acetic acid and a molecule of alkyl acetic acid. Similarly, dialkyl derivative yield a molecule of dialkyl acetic acid and a molecule of acetic acid, for example, N-valinic acid, which can be generated as N-propyl derivative of acetic acid, may be prepared as followed. Similarly, 2-methyl-butanoic acid may be obtained by converting acetoacetic ester into its methyl-ethyl derivative following yield by acid hydrolysis. 7th, hydrolysis of a trihalogen derivative. Trihalogen derivative having all the three halogen atoms attached to a same carbon atom give carboxylic acid on hydrolyzing with alkyl. 8th, oxidation of a methyl ketone haloform reaction. When treating with sodium hypohalites, methyl ketone are oxidized to sodium salt of a carboxylic acid. These salts are acidified to get the carboxylic acid. For example, 2-pentanone plus NaOI give sodium salt plus CHI3 plus 2NaOH in presence of dilute HCl3 butanoic acid give butanoic acid. It may be seen that acid obtained containing one carbon atom less than the starting ketones. 9th, Erdit ester homoligation. This is a convenient method of homoligation of acid such that conversion of a given acid into a next higher homologous. In this method, the acid is first converted into acid chloride by treating with SOCl2. The acid chloride in turn is treated with diazomethane to get a diazoketone. When heated with silver, the diazoketone undergoes Wolff's rearrangement to form a ketanes. These ketanes on hydrolysis give the next higher homologous of the acid. The reaction sequence may be shown as followed. First, for alkoxide, sodium alkoxide react with the carbon monoxide under high pressure to form sodium salt of a carboxylic acid. This yield the free acid on acidification with a dilute mineral acid. Sodium alkoxide plus CO give high pressure dilute HCl give carboxylic acid plus NaCl. Second, from alkene, this method consists in heating an alkene with the carbon monoxide and steam under pressure at 573 to 673 Kelvin in the presence of a phosphoric acid catalyst. For example, ethene plus carbon monoxide plus water in presence of CH3PO4 at 573 to 673 Kelvin temperature give propanoic acid. This reaction involves carboxylation of alkene and is also known as Koch reaction. Note: in addition to method of preparation of carboxylic acid described above, these acids can also be obtained by oxidation of ketones by Baeyer-Williger reaction. Physical properties. Physical state. The lower aliphatic acids such as formic acid, acetic acid and propanoic acid are colorless liquid having sharp irritating smell. The acid from 4 to 9 are colorless oily liquid having somewhat unpleasant smell, but the higher member are colorless, waxy solid having practically no smell. Aromatic acid to exist as a colorless solid. Solubility: the aliphatic acid upon C4 also soluble in water, but the solubility also rapidly with increasing molecular weight and higher acid are practically insoluble in water. Amongst the aromatic acid, even the simplest acid such as benzoic acid is only sharply soluble in water. However, the carboxylic acid are generally soluble in solvents like ether, alcohol, and benzene. The water solubility of a lower aliphatic acid is due to the formation of hydrogen bonding with water in aqueous solution. In higher acids, the size of non-polar alkyl group become larger and the possibility of hydrogen bond formation with water decrease. Formic acid and acetic acid get act as good solvent for a salt because they have a higher dipole moment and can interact with cation and anion. Boiling point: carboxylic acid from intermolecular hydrogen bonding and therefore exists in form of an association molecule. As such, carboxylic acid has high boiling point. The boiling point are considerably higher than those of alcohol as comparable molecular weight. For example, acetic acid boils at 391 Kelvin while N-propyl alcohol boils at 370 Kelvin. This can be attributed to the two reasons. First, OH bond in carboxylic group is more polarized because of the presence of electron attacking carbonyl group in the adjacent position. Therefore, carboxylic acid form stronger hydrogen bonding. Second, the negatively polarized oxygen of a carbonyl group can also form hydrogen bonding with the positively polarized hydrogen of the other molecule. Therefore, majority of a carboxylic acid exists as a cyclic dimer held together not by one but two hydrogen bond as shown below. Fourth, methyl melting point. The melting point of aliphatic carboxylic acid do not follow a regular pattern with the increase in a molecular weight. It is observed that from acid containing upon 10 carbon atom, the melting point of acid containing even number of carbon atom are higher than those of immediately lower as well as immediately higher homologous containing the odd number of a carbon atom. This is called oscillation or alternation effect. For example, the melting point of a butyric acid is higher than of a propanoic acid as well as the valeric acid. This is because acid containing even number of a carbon atom having carboxylic and terminal methyl group on the opposite side of a zigzag carbon chain. As a result, they fit in closely together in the crystal structure. On the other hand, acid having odd number of a carbon atom having the carboxylic and methyl group on the same side of a zigzag chain. As a result, they do not fit so well in the crystal structure. The net result is that the energy required to break the crystal structure and thus melt the acid is more in case of acid having even number of a carbon atom. The melting point of aromatic acid are generally higher than those of aliphatic acid of a comparable molecular weight. This may be due to the presence of uh, due to the reason that planar benzene ring in aromatic acid can fit in more closely in a crystal structure than zigzag chain in aliphatic acid. The melting and boiling point of some carboxylic acid are listed in table 5.2. Chemical properties. The chemistry of a carboxylic acid is governed by the presence of carbonyl group C double bond OH in their molecule. As a result, group may be further looked upon as consisting of a carbonyl group and a hydroxy group. It may be expected to exhibit the reaction of both these groups, but as we shall see, the carbonyl part of a carboxylic group does not undergo its usual reaction with nucleophilic reagent. However, it does influence the behavior of a hydroxy group and is responsible for acidic nature of a hydroxy OH group. The important reaction of a carboxylic acid are discussed as follows. Reaction due to in Ionization hydrogen. Ionizable hydrogen. Cleavage of a OH bond. Cleavage of OH bond. First, acidity. All carboxylic acid ionize in aqueous solution and exist in equilibrium with the carboxylate ion and the hydronium ion. Thus, they exhibit considerable acidic character. The cause of acidic nature of carboxylic acid has been already explained. The acidic constant of a different carboxylic acid and the effect of substituent on acidic are discussed later in section 7.7 and 7.8. Second, salt formation. Carboxylic acid are attached by strongly electropositive metals such as sodium, potassium, and zinc to form their salt and liberate hydrogen gas. They also react with base such as hydroxide, metallic oxide, and bicarbonate to form salts. It may be noted, however, the carboxylate acid are much weaker than mineral acid like hydrochloric acid, sulfonic acid, nitric acid. Therefore, the salt of a carboxylic acid are readily decomposed by treating with above mineral acid to generate carboxylic acid. Reaction involving cleavage of hydroxy group. Formation of a functional derivative. The OH part of acid can be replaced by a number of groups such as Cl, OR, NH2 and OOCr dash to form acid chloride, ester, amide, anhydride, which are collectively known as functional derivative of acid. Third, formation of ester when heated with alcohol in presence of a strong mineral acid such as HCl and H2SO4 or a Lewis acid such as BF3 carboxylic acid from ester. The reaction is reversible in nature and is known as esterification. Carboxylic acid plus alcohol in presence of H positive give ester plus water. The equilibrium in the esterification reaction can be posed in two-word reaction by using one of a reactant in a large excess. It is usually the alcohol which is taken in excess. The formation forward reaction can be further driven to complete if a water formed the reaction is removed stimulatively. This is generally achieved by the using a special design known as Dean dark separation. When the reaction between a carboxylic acid and alcohol to form a ester is carried out in the presence of HCl, it is often called a Fischer-Spire esterification. Relative reactivity of acid and alcohol. The process of esterification is very difficult to carry out if the acid or alcohol used in the reaction carried bulky group near the C double bond OH or COH group. This is because of steric hindrance caused by such groups. Thus, it is very difficult to bring out an esterification reaction involving in a tertiary alcohol. The order of reactivity of alcohol to esterification reaction being primary, secondary to tertiary. Decrease in order of uh, similarly, acid containing bulky groups such as 2,2-dimethyl propanoic acid are difficult to esterify. In fact, special method has to be employed for getting the ester in such cases. The mechanism of a reaction has already been discussed in chapter 1. Formation of acid chloride. On treating with phosphoric pentachloride, phosphoric trichloride or thionyl chloride, hydroxyl group of a carboxylic acid is replaced by chlorine to form acid chloride. Mechanism. The reaction involving nucleophilic attack of a carboxylic acid on phosphorus atom or phosphorus aldehyde or sulfur atom. At the same time, a molecule of HCl is eliminated. The product thus formed undergoes internal nucleophilic attack of a chloride ion on carbonyl carbon to yield the final product. In actual practice, thionyl chloride is preferred to PCl5 or PCl3 since the byproduct of its reaction are gas which escape the reaction mixture. Acid chloride formed can be easily separated from the unreacted thionyl chloride by fractional distillation. For example, butyric acid boiling point 441 Kelvin, thionyl chloride boiling point 352 Kelvin, butyl chloride boiling point 375 Kelvin, SO2 gas and HCl also gas. Formation of amide. When treated with ammonia, acid form ammonium salt which on heating lose a molecule of water to form amide. Formation of anhydride. When treated with acid chloride in presence of a pyridine, carboxylic acid form corresponding anhydride. Mechanism. The reaction is believed to take place by nucleophilic attack of oxygen of a carbonyl acid on acetyl carbon of acyl chloride as shown below. Reaction between sodium salt of acid and acid chloride give better yield of acid anhydride. Mechanism. The reaction takes place through the nucleophilic attack of a carboxylate ion on the carbonyl carbon of acid chloride. Anhydride also obtained by heating monocarboxylic acid with strong dehydrating agent such as P2O5 when a molecule of water is eliminated from two molecules of acid plus H2O. Mechanism. The reaction takes place through the following step. Reaction of a carboxylic acid do not undergo the addition of nucleophilic reagents such as hydroxyamine and hydrazine to form carbonyl compound carbon atom of a carboxylic group. This is because of attacking nucleophile, which is naturally a base, preferable except the acid hydrogen of acid thus lead to formation of carboxylate anion. The carboxylate anion, due to its negative charge and large resonance stabilization, resists the addition of a second molecule of attacking nucleophilic reagent as such as carbonyl group of a carboxylate acid does not form a oximine, a hydrazine or a semi-hydrazine zone. The only important reaction of a carbonyl part of carboxylic acid is its reduction of CH2 as described below. Reduction. Carboxylic acid are ready to catalyze hydrogenation. However, they can be reduced by lithium aluminium hydride to form primary alcohol. The carbonyl part of a carboxylic group get reduced to CH2. The reduced proceed by the formation of alkoxide, which yield the alcohol on hydrolysis. For example, the above method is employed for the preparation of alcohol for acid which are readily available for the natural source. Mechanism. The reaction involving the nucleophilic attack of hydride ion H positive from lithium aluminium hydride on carbonyl compound carbon. The carboxylic acid is reduced initially to aldehyde and finally to primary alcohol as shown ahead. The reduction of acid can also be brought by first converting the acid into ester, which is then conveniently reduced to alcohol. Elimination of a carboxyl group. It is possible to eliminate the carboxylic group from an acid from different product as illustrated by the following reaction. Decarboxylation. Similar carboxylation acid give decarboxylate to form hydrocarbon when their sodium salt are heated with soda lime. Mechanism. The reaction takes place through the loss of a molecule of a carbon dioxide from the carboxylate anion to form an carboanion. Once formed, carbanion get protonated to form a hydrocarbon. Effect of substituent on decarboxylation. Since formation of a carbanion is the key step in the above reaction, any factor which increase the stability of a carbanion should increase the age of decarboxylation. Therefore, carboxylic acid containing electron withdrawing groups such as NO2 and CH3CO get decarboxylate just by heating alone. For example, acetoacetic acid heat करेंगे तो acetone plus carbon dioxide. Similarly, decarboxylic acid containing the two carboxylic groups attached to a same carbon atom are readily decarboxylate. Therefore, decarboxylation of a suitable substituent carboxylic acid such as beta-ketone acid and malanoic acid substituent as an important reaction of a preparative interest. 9. Kolb electrolytic reaction. Electrolytic decarboxylation. Alkyne salt of a carboxylic acid on electrolysis get decarboxylate to form hydrocarbon. It may be recalled that in aqueous solution it is H positive ion which get discharged at the cathode while Na positive ion remain in a solution. The overall Kolb's reaction may be represented as Electrolysis of sodium formate, however, yield only hydrogen and not a hydrocarbon. Thus, 10. Distillation of a calcium salt of acid. When distillation in presence of absence of air, calcium salt of acid yield different product as shown below. Distillation of a calcium formate yield formaldehyde. Second, distillation of a mixture of a calcium salt of formic acid and calcium salt of another carboxylic acid give an aldehyde. Third, distillation of calcium salt of an acid other than formic acid give a ketone. 11th, decarboxylative hydrogenation. Dunsicker reaction. The silver salt of a carboxylic acid react with bromine or iodine in dry carbon tetrachloride to form alkyl bromide or iodine with the loss of a carbon dioxide. Therefore, decarboxylation of a suitable substituent carboxylic acid such as beta ketone acid and malonic acid mechanism. The reaction takes place by free radical chain mechanism as follows. Reaction of alkyl or aryl group. 12. Halogenation of alkyl group. In presence of a small amount of red phosphorus, the alpha hydrogen atom of alkyl group of aliphatic acid can be replaced by chlorine or bromine to a halo acid. This is known as Hilo-Volhard-Gillian reaction, HVZ reaction. It may be noted that bromination takes place exclusively at the beta position and the reaction step after all the alpha hydrogens have been displaced, but chlorination can continue further in the chain after the displacement of alpha hydrogen atom. The reaction is believed to take place as follows. 13. Aromatic substituent. Aromatic carboxylic acid can undergo the usual electrophilic substitution reaction of a benzene ring such as halogenation, nitration, sulfonation. It may be recalled here the carboxylic group is meta-directing and deactivating group and therefore the above reaction takes place only under Vargas condition. It has been studied in earlier classes that the carboxylic group attached to a benzene ring exert an electron withdrawing resonance effect and also electron withdrawing inducing effect minus I and minus R effect. As a result, stability of a carbocation intermediate formed during electrophilic substitution is decreased partially at ortho and para position and consequently electrophilic substitution does not take place easily. Special reaction of formic acid. In the molecule of formic acid, the carbonyl group is attached to a freely hydrogen atom. Therefore, formic acid combines the properties of an acid and an aldehyde as required by the structure. Therefore, it undergoes certain reaction not given by other carboxylic acid. The important reaction of this type are oxidation. Unlike other acid, but like aldehyde, formaldehyde as is readily oxide to carbon dioxide with and water. Therefore, it reduces Tolan reagent to form a silver mirror and filling solution to form a red precipitate of Cu2O. Formic acid also reduces acidified potassium permanganate, acidified potassium dichromate, and mercuric chloride. Second, reaction with concentrated H2SO4. When heated with concentrated H2SO4, formic acid gives CO and H2O. Third, acid of heat on sodium formate. On heating to 663 to 673 Kelvin, sodium formate gives sodium oxalate and hydrogen. Acidic constant and carboxylic acid. It has been already pointed out that in aqueous solution a carboxylic acid exists in equilibrium with the carboxylate ion and the hydronium ion. That is, according to the law of mass action, the equilibrium constant Kc can be expressed by the following expression. Kc is equal to Rc and OO negative into H3O positive divided by carboxylic acid and water. Since water is taken in excess and its concentration remain partially constant, H2O can be omitted from the above expression and relationship can be written as equilibrium constant K is generally referred to as acidic constant since K is directly proportional to a concentration of H3O positive since it would have a low value in case of a weak acid and a high value of a strong acid. In other words, the value of a Ka reflects the acidic strength or acidity of an acid, and therefore Ka can be used for comparing the strength of a different acid. As a comparison to a mineral acid such as HCl, HNO3 and H2SO4, which have Ka value of order 10 raised to power 7 to 10 raised to power 9. Carboxylic acid has a Ka value of order 10 raised to power minus 4 to 10 raised to power minus 5. Thus, carboxylic acid are much weaker acid than mineral acid. pKa value. This day the acidic strength of acid is also represented in term of a pKa value, which is the negative logarithm of acidic constant, that is pKa is equal to minus log Ka. For example, the pKa of acetic acid Ka is equal to 1.75 into 10 to the power minus 5 is equal to 4.75. It may be noted that a strong acid has a larger Ka value but a smaller pKa value, while a weaker acid has a smaller Ka value but larger pKa value. Most of a simple unsubstituted carboxylic acid are of a moderate strength, having pKa value of about 3 to 5. pKa value for some acid are listed in table 5.3 given on a 5.24 page. Effect of a substituent of acidities of a carboxylic acid. The position of equilibrium in the reaction between a carboxylic acid and a furnish carboxylate ion and hydronium ion depend upon the stability of the product of relative to the stability of the reactant. Also, any factor which stabilizes the carboxylate anion more than a parent acid should increase the acidity, and any factor which destabilizes the anion should decrease the acidity. An electron withdrawing substituent on the carboxylate anion attack electron toward itself and thus disperse the negative charge of anion. As a result, it stabilizes the carboxylate anion and thus increase the acidity of a parent acid. An electron releasing substituent on a carboxylate anion intensifies the negative charge of anion and therefore destabilizes the anion. Consequently, it decreases the acidity of the parent acid. In short, it may be stated that electron withdrawing group increase the acidity while electron releasing group decrease the acidity of a carboxylic acid. Shown the effect of a different substituent on the acidity of aliphatic and aromatic acid. Aliphatic acid. Important conclusion. It is quite obvious from the above discussion that first, strong the electron withdrawing group present in acid, the greater is the stability. For example, fluoroacetic acid is stronger than chloroacetic acid because fluorine is a strong electron withdrawing than chlorine. The larger the number of electron withdrawing group present in acid, the greater is the effect on the acidity. That is why we find that trichloroacetic acid is stronger than dichloroacetic acid, which in turn is stronger than monoacid. Third, as a group having electron withdrawing induced effect move always from carboxylic group, its effect on acidity because less pronounced. This is quite in keeping with the fact that induced effect fall off rapidly with the distance. This is where gamma chlorobutyric acid is weaker than beta chlorobutyric acid, which in turn is weaker than alpha butyric acid. Fourth, the effect of electron releasing group is shown in a section D of a table. It is apparent that acetic acid is weaker than formic acid because it contains electron releasing CH3 group attached to a carboxylic group, while formic acid has got only hydrogen attached to a carbonyl group. Aromatic acid, benzoic acid. In discuss the acidities of aromatic acid, let us begin with benzoic acid, which is the simplest and acidic, containing a carbonyl group attached to an unsubstituted benzene ring, such that benzoic acid. Phenyl group directly attached to a carbonyl group exert an electron withdrawing inducive effect, minus I effect, but at the same time it tends to release electron toward the carbonyl group due to resonance effect. Now the plus R effect in this case is more dominating than minus I effect, so that phenyl group has a net electron releasing effect. That is why benzoic acid pKa 4.2 is weaker acid than formic acid. pKa 3.75. It may be noted, however, that the net electron releasing effect of phenyl group in benzoic acid is lesser than the electron releasing inducive effect of alkyl group present in aliphatic acid. Therefore, benzoic acid is a stronger acid than aliphatic acid from acetic acid onward. 5.8.2.2 phenyl acetic acid. Let us now consider the simplest aromatic acid containing the carbonyl group in the side chain such that phenyl acetic acid. Here resonance effect is not possible due to intervening carbon atom between the phenyl and carbonyl group. Therefore, phenyl group exists weakly electron withdrawing inducive effect. Consequently, phenyl acetic acid pKa 4.3 is a stronger acid than acetic acid and higher aliphatic acid containing electron releasing alkyl group. It may be noted that even though phenyl group has electron withdrawing inductive effect, phenyl group which may be treated as phenyl substituent methyl group has the electron releasing effect. As such, phenyl acetic acid is a weaker acid than formic acid. At the same time, electron releasing effect of a benzene group is more than of overall electron releasing effect of a phenyl group. Hence, phenyl acetic acid is weaker than even benzoic acid. 5.8.2.3 Effect of a substituent of acidic strength of aromatic acid. The effect of substituent group present on benzene ring on acidic strength of aromatic carboxylic acid depend upon both of inducive and the resonance effect operating when the group is present in different position as illustrated below. A group having withdrawing inductive effect as well as the electron withdrawing resonance effect such as NO2 group. Let us consider the effect of the presence of nitro group on a benzene ring on acidity of aromatic acid. Nitro group exert an electron withdrawing inducive effect as well as an electron withdrawing resonance effect. However, it may be recalled that resonance effect operate only in ortho and para position, there being hardly an effect on a meta. This means that by the resonance effect, the nitro group cannot markedly reduce the electron density at meta position, although it can reduce the electron density at ortho and para position. At the same time, it can reduce the electron density at all position by inducing mechanism. The net result is that it exerts greater electron withdrawing influence when present in ortho and para position and greatly stabilize the corresponding carboxylate anion. That is why ortho and para-nitrobenzoic acid has a greater acidity than meta-nitrobenzoic acid, which however has greater acidity than benzoic acid. The overall order given below. Effect of halogen. Halogen has a electron withdrawing inductive effect and electron releasing resonance effect, but the inductive effect is stronger than resonance effect. To understand the effect of a presence of halogen on the acidity of aromatic acid, let us take up the case of a para and metachlorobenzoic acid. When chlorine is present in para position, its electron withdrawing inductive effect is opposed effect. Overall effect is electron withdrawing so that carboxylate ion gets stabilized. As a result of para-chlorobenzoic acid is stronger than benzoic acid. When chlorine is present in meta position, only its electron and withdrawing effect inductive effect operate, since there is hardly any resonance effect operating at meta position. As such, there is a strong electron withdrawing effect so that carboxylate ion is much stabilized than in case of a isomer. However, metachlorobenzoic acid is even stronger than parachlorobenzoic acid. Orthochloric benzoic acid is found to be stronger than both meta and para isomer due to ortho effect. Thus, the overall order of acidity of a chlorobenzoic acid are given below. Group C. Group having electron withdrawing inductive effect and electron releasing resonance effect, but resonance effect is stronger than inductive effect, such as CH3 and OH group. For example, let us now consider the effect of a hydroxy group when present in meta and para position respectively in hydroxybenzoic acid. Hydroxy group has an electron withdrawing inductive effect but an electron releasing resonance effect, and its overall effect may be explained as below. Due to the electron withdrawing inductive effect, it tends to decrease the electron density at all positions, but at the same time, it tends to increase the electron density at para position due to resonance mechanism, while the meta position is not markedly affected. Since the resonance effect is more powerful than the inductive effect, the net result is that there is an increase in electron density at the para position. On the other hand, only electron withdrawing inductive effect operates at a meta position, so that there is a decrease in electron density at the meta position. Thus, the hydroxy group present in para-hydroxybenzoic acid exert an overall electron releasing effect and destabilize effect on the carboxylate anion, so that para-hydroxybenzoic acid is weaker than benzoic acid. But in case of meta-hydroxybenzoic acid, hydroxy group exert an electron withdrawing and stabilize influence on the anion, and as such meta-hydroxybenzoic acid is stronger than a benzoic acid. The observed order of a meta-benzoic acid is also similar. D. Group having only electron releasing inductive effects such as CH3 and CH2CH3 group. Such group have acidic weaken effect when present in para and meta position, but the effect is relative more in meta position. Therefore, the order of acidic strength is exceptional behavior ortho effect. As usual, observation is that practically all groups when attached ortho to a carbonyl group in or aromatic acid increase the acidity. This anomalous behavior of a group when present in ortho position is known as ortho effect. However, it has not yet been possible to explain their behavior completely. The acidity of some simple and substituent aromatic acid are given in section E of table 7.3. Test of a carboxylic acid. Carboxylic acid can be detected by the following test. Carboxylic acid turn blue litmus to red. They get influence with the liberation of a carbon dioxide when added to a solution of a sodium bicarbonate. When a carboxylic acid is heated with alcohol in presence of a small quantity of concentrated sulfuric acid, a pleasant smell is produced due to formation of ester. Thank you. This chapter is complete.